Section 2.6. Limits at infinity. There are two parts to this section. The first part is limits at infinity, and the next part is infinite limits. So first, let's look at limits at infinity. And I want to start by writing the definition. But as I write the definition, I'm going to say it in simple English. So you can make the relationship between those mathematical symbols and what it really means to us in layman's language. So we're going to write this statement. The limit as x approaches infinity of f of x equals a number L means that given epsilon greater than 0, however small, okay, there is a number m, positive, such that but what does it mean for x to go to infinity? X going to infinity means x can grow and grow and grow, right? Which means you give me any number, okay, x is going to be greater than that number. Okay? Because x is growing, okay. So given epsilon greater than 0, there's a number m such that x greater than m implies that this function value is as close to the limit as I want. Okay? All I have to do is just make x larger. The closer I want f to be to L, the larger I make x. Okay? Well, let's look at a picture here. Okay, let's see. The limit as x goes to infinity of 1 over x, right? So when x is getting larger and larger and larger, what happens to its reciprocal? It gets smaller and smaller, right? And as a matter of fact, how can I make this really small? Make x really large, right? And so I can make this as small as I want. What is that number that approaches? 0. Okay? So that's what I was trying to say over here. That I can make this limit, the function value 1 over x, as close to 0 as I want. All I have to do is make x really large. And the closer to 0 I want this to be, the larger x needs to be. And so forth. Now if you remember the picture for 1 over x on the positive quadrant, this is what it looks like. And so here's some pictures of x going to infinity. And if you take that same triangle position here, right? As x goes to infinity, you're going to slide down this curve. And here's the y value for that triangle. Right? And as you slide down that curve, the y value gets close to what number? 0. So the limit as x goes to infinity describes the behavior of my function to the far right side of the graph. We have something similar for the left side. This is the other definition. So the limit as x approaches infinity, or negative infinity, of f of x equals L if given epsilon greater than 0, no matter how small, there exists a number n less than 0 such that x less than n implies f minus L less than epsilon. Okay? a similar picture for that limit. Let's look at the same function, 1 over x. Right? As x gets larger and larger in the negative direction, like we're talking like negative a million, right? The reciprocal is negative, but it's really small. Right? The reciprocal is negative, but it's really small. And here's a picture for 1 over x in the negative quadrant. Okay, again, x going to negative infinity means you're running to the far left on the x-axis. And on the curve, right, you're rising up and you're going to 0. Right? As this triangle moves up on the curve, the y values are getting close to 0. Okay? Now this is a good demonstration of how we can demonstrate the definition of epsilon delta. So let's come back here and talk about, well, there's no delta here, there's an m, but let's talk about how epsilon comes in. Okay? So I'm going to use this same graph. Let's take a look at this. Right? What is my limit in this case? My limit is 0. So saying 1 over x minus f of x minus L less than epsilon, right, is the same as saying 1 over x less than epsilon. And we don't need absolute values because we're talking about x going to infinity. So surely it's positive. So 1 over x less than epsilon, that means that the y value has to be less than epsilon. So here's 0. Let's say that much is epsilon. Right? So you come here, and that gives you an x value. According to the graph, if I want my y value to be within epsilon away, what part of the x-axis do I have to occupy? To the right of that, right? Because the further right I go, the closer to 0 I get, so I'm within epsilon away. That's the number m I'm talking about in the definition. Okay? That if I want my y values to be epsilon away from the limit, which is in this case 0, okay, this is the limit, then I just have to find an m so that after that, when x is larger than m, which means to the right of that, my function values will be within epsilon away from 0. Okay? I'm going to do the same thing for the other one here. So here, let me say that this distance is epsilon. Right? Then all I have to do to make sure that my function values are epsilon away from the limit, I have to find a number n, which is negative, so that after that, or to the left of that number, my function values will be within epsilon away. Okay? Is that clear? Okay. But I'm not going to get into too much of the proofs with the epsilons for infinite limits. As a matter of fact, almost all of the limits that we're going to compute where x is going to infinity or negative infinity, we will be using this theorem that I just established. So this theorem meant something very similar to it. So here we go. Theorem. The limit as x goes to plus or minus infinity if 1 over x is 0. Okay? That's the first part of the theorem. The second part of the theorem is that the limit as x goes to plus or minus infinity of a constant is equal to the constant itself. Let's look at a picture for 2. Okay, so So say we have a constant here, k. The graph of y equals to k is a horizontal line. And as x gets larger and larger, we're just traveling to the right. And as we do that, our y values are still k. Okay? Same thing on the left side. So as x goes to infinity of a constant is just a constant. These two theorems together will help us evaluate infinite limits for a lot of different complicated functions. Okay? Here's an example. Let me write a note first. This theorem, along with the limit laws established earlier, suffice to compute limits at infinity. Okay. By limit laws, I'm talking about the limit of a sum is the sum of the limits, limit of the product is the product of the limits, etc. So those two theorems, along with those other laws, suffice for most of the calculations we're going to do.